All right, section 20.2 is going to focus on voltaic cells. Now, what we can remember from section 20.1 is anytime we have an ox-redox reaction, electrons are transferred. When electrons are transferred, energy is released. So how do we harness this energy? Well, this is kind of how the idea of a battery or a hydrogen fuel cell works. So if we can figure out a setup to get these flow of electrons to produce energy, we have produced a battery. And a battery is just a battery is a type of voltaic cell. So if we can figure out a way to get these electrons moving, we can create a voltaic cell. And typically, what a cell looks like is this. The oxidation occurs at the anode. So the oxidation is occurring at the anode, the negative part. The reduction is occurring at the cathode, the positive part. All right? So again, the oxidation is occurring at the anode. The reduction is occurring at the cathode. So kind of something to think here. And what we have is the movement of cations and the movement of anions. And we have the move of charge, like electrons, the move of electrons, we've created a battery. What happens is once you get the flow going, and it's not going to be a balance, the flow of electrons is going to stop once your balance of electrons is gone. Therefore, what we have to do to make sure that we have electrons continually in the solution is we have to use a salt bridge. And what a salt bridge is, it's a U-shaped tube that contains a salt solution that helps keep the charges in each beaker balanced. So what we have here is you can see the salt bridge is this U-shaped tube of sodium nitrate in this picture, in this diagram. So the cations are going to move towards the cathode, the anions will move towards the anode, and it's going to help keep our charges balanced. If our charges aren't balanced, the battery goes dead. And that's essentially how a voltaic cell or a battery can go dead. So, in the cell, electrons leave the anode and flow through the wire to the cathode. As the electrons leave, the cations dissolve into the solution to kind of make up for the loss of charge. As the electrons leave the cathode, the cations in the cathode are attracted to the negative cathode. The electrons are taken by the cation, and the neutral metal is deposited on the cathode. Now, when we talk about voltaic cells, we're going to talk about volts. Now, volts in electricity is kind of how electricity travels or how our electrons travel. So think of it this way. Water only flows one way in a waterfall. Electrons are the same way. Electrons are going to flow one way in a redox reaction, from higher to lower potential energy. From higher to lower potential energy. Think of it like a waterfall, high to low. That's the same exact way that electrons are going to travel in a voltaic cell, from high energy to low energy. Now, what we can do is we can calculate essentially how high the waterfall is. And this is called the cell potential, and it's designated as E cell. Sometimes it's called the potential difference is the electromagnetic or electromotive force, EMF. Typically, you'll see it called the cell potential. And the cell potential is how high the waterfall is. The higher the waterfall, the larger the difference, and the more energy that cell has. Cell potential is measured in volts. You may have heard volts before. Volts should be nothing new to your vocabulary. The unit for a volt is 1 joule over C. All right, typically we're going to do volts, and we're going to explain how we can figure out the volts for a voltaic cell or for a battery. What we have here is we have the measured voltage for a variety of reduction reactions. So you can see here some of them are positive, some of them are negative. Their values are referenced. All right, so by definition, the reduction potential for hydrogen is 0 volts. If we want to, outside of hydrogen, if we want to calculate the cell potential for any other cell, if we're going to have a redox reaction and I want to figure out how much energy could be created in my voltaic cell, we're going to take the energy of reduction of the cathode, the energy of reduction of the anode, we're going to subtract the two. and that is going to be the amount of voltage or the amount of potential energy that exists in that cell. So the energy of reduction of the cathode minus the energy of reduction of the anode. So for the oxidation in this cell, the E reduction is negative 0.76. For reduction, it's positive 0.34. Now remember, the reduction is the cathode, the oxidation is the anode. So we're going to take 0.34 minus a negative 0.76, and we're going to find out that the possible cell potential for this battery is 1.1 volts. We're going to do a couple of examples with this in class as we talk about developing a voltaic cell, how we do it, and calculating the E cell that can exist. A couple of final things when we talk about voltaic cells. The strongest oxidizers have the most positive reduction potentials, and the strongest reducers have the most negative reduction potentials. If you can find the most dramatic difference between the two, you've just created the strongest battery. Now, you may see this lithium at the bottom, strongest reducing agent. What are batteries? Some batteries made out of lithium ions. Why? You can see here it's a very strong reducing agent, so it's possible to create a very large cell difference or potential energy in the cell using an ox-redox reaction. The greater the difference between the two, as I mentioned, the greater the voltage, hence why lithium is a sought-after material for you making batteries and other voltaic cells. So that concludes section 20.2, voltaic cells.